Today I wanted to shoot a video about shocks and springs and some stuff that I've seen that's kind of going on lately. I want to explain through rod shocks, my take on it, and spring frequencies. So let's roll the intro and let's talk a little bit about shocks, springs, spring frequencies, and through rod shocks. I've spent the last 30 plus years working on race cars, building race cars, and racing cars. And I'm here to help you better understand racing technology. The first thing I wanted to talk about today are the through rod shocks. And basically what a through rod shock is when you have a gas pressure shock, the gas in the gas pressure, the nitrogen, is used to take up the volume of the shaft going in. So with a through rod shock, the shock rod passes all the way through the shock. Whatever goes in one end goes out the other end, negating the problem of having a gas pressure behind it to kill the cavitation and to take up the volume of the shaft. The problem with through rod shocks is they don't often allow for heat expansion. Heat expansion will actually deaden or lock a shock. Maybe these shock manufacturers now have figured out a way to get around this whole deadening procedure. I don't know. I don't look really at what is going on now. I just know them in theory. But there are problems with through rod shocks. But that doesn't matter because all the sanctioning bodies have come along and killed that technology before it could really even get off the ground. And it's getting annoying on how these sanctioning bodies kill all these suspension ideas, but they do nothing about car costs or engine costs or tire costs. Those are all left unchecked for the bigger companies to make a ton of money. But the innovating racer or a shock company or something like that making a better product gets killed instantly. And it's getting sickening. What a lot of old school guys used to do to kill this gas pressure is when the monotubes were first coming out with the nitrogen gas pressure, everybody was trying to lower them. They hadn't, a base valve wasn't really figured out too good yet. And what the old school guys used to do is keep a pair of emulsion twin tube shocks, which are no gas pressure. The internals on them basically were, as the shaft went in, there was a gas bag separating the fluid from the rest of the air inside the shock. As the shock shaft went in, the gas bag compressed a little bit and there was no gas pressure. Now I don't think anybody really even wants to run a emulsion type of twin tube shock anymore, but they did have merit back in the day. Now everybody's on monotube. One way you can kill gas pressure in a monotube shock is by making the canister bigger. And I don't know why shock companies don't start doing this now that they killed the through rod shock thing. The bigger you make your canister, a lot of canisters are small. The bigger in diameter and the larger gas volume you have in a canister, as that rod goes in, the bladder or the piston, I think most of them are bladder shocks now, with the bladder and the piston would actually compress a little bit and take up the volume of the shaft. or the floating piston would move a little bit to take up the volume of the shaft. But as that piston rod would go into the shock, and the gas volume would actually start to decrease, it would actually increase on rod pressure. The smaller the volume is on your remote reservoir, the more the gas pressure will build as the shock gets compressed. Now, a way to get rid of this, if you want to drop your gas pressure down, is to just put a bigger canister. So as that shock rod goes in, that piston or that bladder doesn't have room as much, and the increase in nitrogen pressure isn't going to be as drastic on a big canister than a small canister. So I would hope that as time goes along, shock manufacturers, now that they're being kind of handcuffed, would start making their remote reservoir chambers bigger and bigger to allow for a lower gas pressure and a lower gas creep pressure as the shaft is compressed. As a matter of fact, I would recommend any racer that really wanted to innovate and they had a machine shop that was their sponsor, they ran a machine shop, start making your own parts for these. Now that we're going to a gas bladder, you don't have to have the internal section of your remote reservoir hard-coated. You used to have them hard-coated or plated so when the piston moves on them it doesn't wear or it doesn't hang up. It had to be a smooth hard coating thing. But now that we're using so many gas bladders in there and everything else, there's no need for that hard coating on the inside. So for a machine shop, a good machine shop, to turn out a larger diameter gas chamber would be pretty easy. You know, you have to figure out your threading and how to figure it all onto an existing compartment, but I deal a lot in Integra stuff, and I know in a remote reservoir on an Integra shock, that remote reservoir is separated. All you'd have to figure out is basically how to attach a gas bladder in there and have a machine shop crank those things out. It'd be pretty easy for a good machinist. Okay, this is where I do a book plug. If anybody is interested on getting in on the core builds of a shock absorber, how they work, and places, if you want to start building your own shock pieces or innovating on a shock, try picking this book up. It's right here. It might be expensive. I bought it. It might be expensive. I bought it several years ago. It's been sitting around. I paged through it. I read parts of it, many parts of it. It's very math and very engineering intensive, but everything you're going to want to know about building a shock at their core principles is going to be in this book. So if you're into geeking out on shocks, it might be something for you. The next thing I wanted to talk about is springs. And springs and shocks run hand in hand, and there are some things about springs I've been thinking about lately because all the rules are getting squashed and tied so tightly that springs might be becoming a very big deal within the next couple of years. And the big deal I'm talking about is spring frequency. See, when you have a spring, the larger the diameter, the smaller diameter, all affects the frequency. I'll have a drawing here later and I'll illustrate frequencies for people who kind of don't understand that. It's real easy. It's not nothing technical. But I'll explain it a little bit more and how it relates and how it impacts our racing. Like I said, as our racing gets closer and closer, and the car's getting closer and closer to an IROC car now, we have to start splitting hairs. So I think a good place to understand and to start understanding is spring frequencies. And there is a difference in frequencies. See, what a frequency is the amount of time, if it's frequency and amplitude. Amplitude is the height that the tire would travel. So on a really rough track, the amplitude would be very, very high. High amplitude with a very low frequency. That means that when that tire goes up and comes back down, the amount of time that it takes that tire to travel that is a frequency, and the amplitude is the height. So on a rough track, it has a low frequency and a large amplitude. On a slicker track, like a blackened off track, the frequency is high, but the amplitude is low because the tire doesn't have to travel as high anymore. The tire only has to travel like this. So there is a difference in spring frequency. The larger your wire is on your springs, the more frequency, or the higher the frequency is on those springs. Let's think about this in terms of spring stacking now. If you put a single spring, let's just take the right rear for example. You put a 200-pound right rear spring in it. Just base numbers, I think they're up around 250, 275 now, whatever. But if you take a 200-pound spring and you put it in that right rear single spring, it will probably have a lot of free height between the coils. It'll be a higher amplitude and a lower frequency spring. But now as the track dries out, how would you get a spring? Let me back up a minute. The problem with higher amplitude, lower frequencies is when that thing, it's a lag difference. So lower frequency spring will not actually return. It takes time to return back to position. They're lazier, basically, is what it boils down to. So as a track dries out and you want a spring to actually react real fast, and you want to go to a higher frequency suspension or something, you're going to have to increase your wire diameter to get into your higher frequency springs to match the higher frequency track, lower amplitude. And it's getting very complicated. But I want to just cover this a little bit because now we're going to get into spring stacking. Is it better to stack a spring to get your higher frequency, lower amplitude when the track dries out? You take your high amplitude, low frequency 200 on the right rear. Now the track dries out and you want to go to a higher frequency on that right rear, but still maintain that 200-pound spring change. You still want to maintain that 200-pound spring on the right rear. What you can do is you can stack two 400-pound springs on top of each other. We're not talking about lockouts or anything like that. Just stacking two 400-pound springs on the right rear will increase the frequency of that right rear, because on a 400-pound spring the wire diameter is bigger, which will increase the frequency. So when you stack them together, it'll still be 200 pounds per inch. But now the frequency has increased and the amplitude has decreased, making it a better traction on the right rear. I think this would need some experimenting, but if I were really into the racing thing now, I help out some cars, but on a local level, a lot of guys aren't thinking about this now. But I think there is room here to talk about this and to start thinking about this if you're running in a very, very hyper competitive environment where the track changes a lot throughout the night. You might want to have two setups for your right rear, one being a low freak and the other being a high freak. Years ago, shock manufacturers, when they were building shocks, they used to have basically a high frequency setup for their shocks, and they'd have a low frequency, and they call them either rough track or dry track shocks or whatever. But this may be coming back because of the hyper competitive nature of the racing now. So let's go over to the drawing board, and I'm going to explain, and I'm going to draw out a picture. Still no computer rendering this week, so it'll be a hand sketch picture. But I'm going to explain a little bit more visually about frequency and amplitude and how it works with your wheels and with your suspension. So let's head on over there. One little side note I wanted to get into a little bit before we got really into the frequency thing is shocks ideally should be matched to the frequency. So what we might end up seeing is these sanctioning bodies want to cut costs on suspensions, but to really get into it, you'll probably need two sets of shocks in your trailer, a high frequency and a low frequency shocks, which will actually add to the cost of your entire program. But this is where we are. So this is what is going on with this. This is basically 1 second of time on both timelines. A high amplitude, low frequency shock would be large wheel travel. This represents the travel of the tire, the travel of the axle, or whatever you're dampening there. On a high amplitude, low frequency, the amount of distance it's going to travel will be high. On a high frequency, low amplitude, like a slick, shiny track, it will actually, the tire and axle travel more at a higher frequency, but it will be the same time. It just won't be as tall. Because the track is smoother, it doesn't have to go up like this. It just has to make smaller paths. So this is what's considered a high frequency, low amplitude, shiny, slick type of deal. This would be a higher amplitude, lower frequency, rough and muddy type of deal. Like I said, to optimize this, then this would have to be matched with your springs and your shocks, because you can valve these shocks to be either low frequency, high frequency, rough track deals, slick track deals. So as you change the frequency of your springs on like your right rear is probably where I'm thinking this is going to be the most important. Probably, then you're going to move to your right front and then your left rear. But this is where we are at with it. If you like this video, subscribe to my channel and hit the like button. That really helps me out. But what the subscribe does is whenever I get a new video out and you get onto YouTube looking for stuff to see, it'll just pop up a little notification that I got a video out and you can come and watch it. So hit the subscribe button, like button, and I will see you in the next video.